Tonight, we're going to talk about something that will completely change how you experience sitting still. Right now, as you're watching this, you're on a journey through space, an extreme one. Not metaphorically. Literally. You are moving through the universe at speeds so large that they are almost impossible to imagine, yet you feel none of it. No vibration. No wind. No sensation of motion at all. And by the end of this video, you won't just know that you're moving, you'll understand why you can never feel it, and why stillness is something that doesn't actually exist in nature. Before we begin, take a moment to consider something simple. If everything around you is moving with you, how would you ever know you're moving at all? That question is where everything starts. 1. The illusion of stillness. From the moment you wake up to the moment you sleep, your brain tells you a simple story. You are standing still. The walls are still. The ground is still. The room is still. But that feeling is not reality. It is a carefully constructed illusion created by your nervous system. Your senses do not measure absolute motion. They measure change. They measure differences between you and your surroundings. If everything around you moves together, your brain receives no signal of motion at all. This is why you can sit in a plane traveling at 550 miles per hour and drink a cup of water without it spilling. Inside the cabin, nothing feels fast. But outside that window, the earth is racing beneath you. Now zoom out from that airplane. Because the airplane is sitting on something far more extreme, a rotating, orbiting, solar system-driven, galaxy-moving platform that never stops. You are not stationary. You are layered motion. And each layer is faster than the last. 2. Earth's rotation, the first invisible speed. Let's start with the most familiar motion, Earth's spin. The Earth rotates once every 23 hours, 56 minutes, and 4 seconds. That is called a sidereal day. Not 24 hours. That extra difference exists because Earth is also moving around the Sun while it spins. Now imagine standing on the equator. You are sitting on a rotating sphere with a circumference of about 24,901 miles. That entire distance is completed in a single day, which means you are moving at approximately 1,040 miles per hour. That is faster than the speed of sound. And yet, you feel nothing. No wind. No force pushing you sideways. No sense of spinning. Why? Because everything around you is moving at the same speed. The ground beneath your feet. The air in the atmosphere. The buildings. The oceans. Your own body. There is no relative motion to detect. Now here is something even more interesting. That speed is not the same everywhere on Earth. The farther you move from the equator, the slower your rotational speed becomes. At the poles, you are essentially rotating in place. Not because Earth stops spinning there, but because the radius of your circular motion shrinks. This is geometry shaping your experience of motion. But we can go deeper. Because this rotation does something else subtle. It creates an invisible force called the Coriolis effect. 3. The Coriolis effect, Earth's hidden force. The Coriolis effect is why hurricanes spin. It is why winds curve instead of moving in straight lines. It is why ocean currents form massive rotating systems, but it is not a force in the traditional sense. It is the result of being on a rotating sphere. Air moving from one part of Earth to another does not travel in straight lines relative to the surface, because the surface beneath it is constantly shifting sideways. This is also why large-scale weather systems rotate differently in the northern and southern hemispheres. One spins counterclockwise. The other spins clockwise. Not because storms decide to spin that way, but because you are living on a rotating frame of reference. Even something as chaotic as a hurricane is shaped by the motion of the planet itself. And yet, you still do not feel Earth spinning, because you are not moving through Earth. You are moving with Earth. 4. Why we don't fall off a spinning planet. A common question appears here. If Earth is spinning so fast, why aren't we flung into space? The answer is gravity. Gravity pulls everything toward the center of Earth with a force far stronger than the outward effect of rotation. At the equator, the outward centrifugal effect is only about 0.3% of gravity. Gravity wins by a massive margin. That is why you stay grounded. Not because Earth is still, but because you are being held in place while it moves. Now we move outward again. Because rotation is only the first layer. 5. Earth's orbit, 66,600 miles per hour. Earth is not only spinning, it is also falling around the Sun. This is orbit. Orbit is not moving forward in a circle. Orbit is continuous freefall, where forward motion and gravitational pull balance each other perfectly. Earth is constantly falling toward the Sun. But because it is moving sideways so fast, it keeps missing it. This creates a stable orbit. The result? Earth travels about 584 million miles every year, which means Earth is moving around the Sun at 66,600 miles per hour. That is 30 times faster than the fastest jet ever built. And again, you feel nothing. No acceleration. No shaking. No directional force. Because you are not moving through space alone. You are moving with the entire Earth-Sun system. Even the atmosphere is orbiting with you. There is no wind caused by this motion because there is no relative difference in velocity. Now here is something deeper. If Earth suddenly stopped orbiting the Sun, everything on the surface would be catastrophically affected. But because everything shares the same orbital motion, it is invisible. This is the principle of inertial frames. A system moving at constant velocity cannot detect its own motion internally. This idea was first clearly described by Galileo, and it changed physics forever. 6. The Galileo ship analogy. Imagine you are inside a closed room on a ship. The ship is moving smoothly across calm water. Inside the room, you drop a ball, it falls straight down. You toss something, it behaves normally. You drink water, it stays still. There is no experiment you can do to prove you are moving. Unless the ship accelerates, everything feels identical to being at rest. Earth is that ship. except it is not moving across water. It is moving through space itself. 4. 7. The Sun's journey around the galaxy. Now we expand again. The Sun is not stationary. It is orbiting the center of the Milky Way galaxy. And this orbit is enormous. The Sun is about 26,000 light-years from the galactic center. It takes roughly 230 million years to complete one full orbit. That means dinosaurs did not exist the last time the Sun was in a similar position. And the next time it completes a full orbit, Earth will be completely unrecognizable. The Sun's speed through the galaxy: 490,000 miles per hour. 500,000 miles per hour. And you are moving with it. Right now. Every second, the Sun moves about 136 miles through space. But you do not feel it. Because again, everything around you shares the same motion. 8. Why space doesn't create wind. On Earth, motion through air creates wind resistance. But in space, there is almost no medium. Space is not completely empty, but it is so close to a vacuum that drag is effectively zero. No friction. No air resistance. No cosmic wind. So even at hundreds of thousands of miles per hour, nothing slows the solar system down in any noticeable way. 9. The galaxy's motion, over 1 million miles per hour. Now we zoom out further. The Milky Way galaxy itself is moving. Not just rotating. Not just orbiting, but traveling through space relative to the cosmic microwave background, the afterglow of the Big Bang. By measuring tiny temperature differences in that radiation, scientists discovered something extraordinary. The entire galaxy is moving at about 1.3 million miles per hour toward a region of space shaped by gravity from massive cosmic structures. And you are part of that motion. Right now, you are moving over 1 million miles per hour through the universe. And you cannot feel it. Not even slightly. 10. The cosmic web and large-scale structure. The universe is not random. Galaxies are arranged in filaments, walls, and clusters. A structure known as the cosmic web. Gravity pulls matter into long threads spanning hundreds of millions of light-years. Between them are enormous voids, regions almost completely empty. Everything is in motion. Everything is falling towards something else. Even the Milky Way is not moving freely, it is being pulled by larger structures like galaxy clusters and superclusters. But even these are not final. Because the universe itself is expanding. 11. Expansion of space itself. This is where intuition breaks. Galaxies are not simply flying away from each other. Space itself is stretching. Like dots on a balloon being inflated. The dots are not moving across the surface. The surface itself is expanding. This means distant galaxies appear to move away faster the farther they are. At extreme distances, galaxies recede faster than light, not because they break physics, but because space itself is expanding. This creates the observable universe. About 46.5 billion light-years in every direction. Beyond that, light will never reach us. 12. why you still feel nothing. At this point, the question becomes unavoidable. If all of this motion is real, why do we feel nothing? The answer has 4 layers. 1. Everything around you shares the same velocity. 2. Motion is only detectable through acceleration. 3. The accelerations involved are extremely small compared to gravity. 4. There is no medium in space to create resistance. Gravity dominates everything you experience physically. Even a car feels fast not because of speed, but because of acceleration. Cosmic motion is smooth, and smooth motion is invisible to your senses. 13. Interstellar travel, the next challenge. Now we scale outward again. Traveling to other stars is not just about distance. It is about motion. Every star is moving. The sun is moving. The galaxy is rotating. Nothing is fixed. Even the nearest star systems will have shifted position by the time a spacecraft arrives. At current speeds, even our fastest spacecraft would take tens of thousands of years to reach another star. So trajectories must account for stellar motion, galactic motion, orbital mechanics, relativistic effects. Space navigation is not pointing and flying. It is predicting the future position of moving targets across time. 14. Relativity, when space and time change. As speed increases toward the speed of light, strange things happen. Time slows down. Distances contract. Mass increases relative to motion. A spacecraft traveling at 90% the speed of light experiences time very differently than Earth. At 99%, a journey of years might feel like months. These effects are not theoretical. They are measured and proven. They are already accounted for in GPS satellites orbiting Earth. Even navigation on Earth depends on relativity corrections. 15. The future collision of galaxies. The Milky Way is on a collision course with Andromeda. They are moving toward each other at hundreds of thousands of miles per hour. In about 4 billion years, they will merge. But it will not be a violent crash. Space is mostly empty. Stars will pass through vast distances without colliding. The galaxies will slowly merge into a single new structure. A new galaxy, sometimes called Milkomeda. And through it all, motion continues. 16. Final revelation, there is no still point. Now step back. Everything you have learned points to one conclusion. There is no absolute rest in the universe. No universal fixed point. No true stillness. Only motion relative to something else. Earth rotates. Earth orbits. The sun moves. The galaxy moves. Space expands. And you move with all of it. Right now. At speeds beyond 1,000,000 miles per hour. Without ever feeling it. Because you are not separate from the motion. You are part of it. There was no other way to explain the effect. If Earth were stationary and the sun orbited it, there would be no aberration. The stars would remain fixed in position throughout the year, but they don't. Their positions shift in a pattern that matches Earth's orbital motion. This was one of the first direct proofs that the Copernican model of the solar system was correct. Stellar aberration affects every star in the sky. The amount and direction of the shift depends on a star's position and Earth's velocity. Stars near the ecliptic show the maximum effect, while stars near the poles show less. Modern telescopes must correct for this effect with extreme precision. The Hubble Space Telescope accounts for aberration when targeting distant galaxies. Without correction, it would point slightly off target. Even a tiny error becomes significant at cosmic distances. The Gaia spacecraft takes this even further. It is mapping over 1 billion stars with precision down to microarcseconds. At that level, it must correct not only for Earth's motion, but for the Sun's motion through the galaxy as well. The Sun itself is moving at hundreds of thousands of miles per hour relative to nearby stars. This creates a second, larger aberration effect. By correcting for all of this, Gaia is building the most precise 3D map of the Milky Way ever created. And what it reveals is simple but profound. We are not stationary. We are moving through space in multiple layers of motion at once. That leads to something even deeper: time. According to Einstein's theory of relativity, motion affects time itself. This is called time dilation. The faster you move, the slower time passes for you relative to someone at rest. At everyday speeds, the effect is so small it is unnoticeable. Earth orbits the Sun at about 67,000 miles per hour, fast in human terms, but only a tiny fraction of the speed of light. At that scale, time slows by only nanoseconds per year. Completely invisible in daily life. Even the Sun moving through the galaxy produces an effect too small to matter in practice. But as speeds increase, something dramatic happens. At 10% of light speed, time slows slightly. At 50%, it becomes significant. At 90%, time runs far slower. And as you approach the speed of light, time dilation becomes extreme. Years for one observer can become months or even days for another. This is not theoretical fiction. It has been measured. Muons, tiny particles created in Earth's upper atmosphere, should decay before reaching the ground. Yet they do reach the surface because they are moving so close to the speed of light that time slows down for them. Their internal clock runs slower, allowing them to survive long enough to be detected. Relativity is real. And it leads to a hard limit. Nothing with mass can reach the speed of light. As you accelerate closer to it, the energy required rises dramatically. At 99.9% of light speed, an object behaves as though it has over 20 times its normal mass from an outside perspective. To reach light speed would require infinite energy. Only light itself can travel at that speed. Now, even though these effects are tiny in daily life, motion still affects the world around us in important ways. GPS is one of the clearest examples. Satellites orbit Earth at high speeds and at higher altitudes than us. This creates two competing relativistic effects. Special relativity slows their clocks. General relativity speeds them up due to weaker gravity. The net result is a timing difference of about 38 microseconds per day. That sounds small, but GPS depends on nanosecond accuracy. Without correcting for relativity, navigation errors would grow by miles every day. your phone would quickly become useless for directions. Every GPS system on Earth is a working confirmation of Einstein's theory. Another consequence of motion is cosmic radiation. Earth is constantly hit by high-energy particles from space, traveling close to the speed of light. Most are blocked by the atmosphere and magnetic field, but some still reach the surface. At higher altitudes, exposure increases dramatically. Astronauts in space receive much higher doses of radiation, and long missions, like trips to Mars, pose serious challenges because of this constant exposure. Then there is the cosmic microwave background, the afterglow of the Big Bang. Because we are moving through space at over 1,000,000 miles per hour, the CMB appears slightly hotter in the direction we are moving and cooler in the opposite direction. This tiny difference allows scientists to measure our motion through the universe itself. On the largest scale, the universe is expanding. Distant galaxies are moving away from us not because they are traveling through space, but because space itself is stretching. The light we see from them is ancient. Some of those galaxies no longer exist in the form we observe. In the far future, most galaxies will disappear from view entirely as expansion carries them beyond our cosmic horizon. The universe we see today is only a snapshot of what once was. This brings us to a deeper realization. For most of human history, we believed Earth was the center of everything. That belief slowly unraveled. First, Earth orbits the Sun. Then the Sun is just one star among billions. Then the galaxy is one of trillions. Now we know there is no center at all. We are not stationary. We are not central. We are moving through a vast and expanding universe. But there is another side to this story. Even though we are small, we are aware of it. We can measure our motion. We can calculate it. We can build machines that detect it across billions of light years. We are the universe becoming conscious of itself. Everything you are made of, every atom in your body, was forged in stars that lived and died long before Earth existed. Those atoms have been traveling through space for billions of years before becoming you. You are not separate from this motion. You are part of it. So when we ask how fast we are moving through space, the answer depends on perspective. Relative to Earth's surface, almost still. Relative to Earth's rotation, about 1,000 miles per hour. Relative to the Sun, about 67,000 miles per hour. Relative to the galaxy, about 490,000 miles per hour. Relative to the cosmic background, over 1,300,000 miles per hour. All of these are correct. There is no single true speed. Only relative motion. And that is one of the deepest truths in physics. Everything is moving. Everything is changing. Earth will slow its rotation. The moon will drift away. The sun will evolve. The galaxy will collide with others. The universe will continue expanding. Nothing is permanent. But right now, you are here, sitting still relative to your surroundings, while riding a planet that is racing through space at unimaginable speed. And you cannot feel it. That is the quiet strangeness of reality. You are not standing still. You are moving through the cosmos. Right now. Even beyond everything we've talked about, motion through space creates effects that scientists are only beginning to fully understand. Take gravitational waves. For centuries, gravity was thought of as an invisible force acting instantly across space. But Einstein changed that picture completely. According to general relativity, gravity is actually the curvature of spacetime itself. Massive objects bend the fabric of reality around them. And when extremely massive objects move violently through space, they create ripples in spacetime. Those ripples are called gravitational waves. Imagine dropping a stone into a pond. Waves spread outward across the water. In a similar way, when black holes collide or neutron stars spiral together, they send waves traveling across the universe at the speed of light. These waves stretch and compress space itself. Everything moves slightly closer together, then slightly farther apart. The effect is unbelievably tiny. When the first gravitational wave passed through Earth in 2015, the amount of stretching was smaller than the width of a proton. Yet scientists still detected it. The discovery came from LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses laser beams traveling through enormous vacuum tunnels 4 kilometers long. The lasers bounce between mirrors with incredible precision. If a gravitational wave passes through Earth, the distance between the mirrors changes by a tiny fraction. That's exactly what happened on September 14, 2015. Two black holes about 1.3 billion light-years away collided and merged into one larger black hole. In the final fraction of a second before merging, they were orbiting each other at nearly half the speed of light. The collision released more energy than all the stars in the observable universe combined during that instant. That energy traveled across space as gravitational waves. After journeying for 1.3 billion years, those waves finally reached Earth and slightly distorted spacetime itself. Humanity detected them. For the first time in history, we weren't just looking at the universe. We were listening to it. This opened an entirely new way of studying motion in the cosmos. Before gravitational wave astronomy, black holes were invisible unless they interacted with surrounding matter. Now we can detect black holes colliding directly through the motion they create in spacetime itself. We've since detected dozens of gravitational wave events. Black hole mergers. Neutron-star collisions. Possibly even signals from objects we don't fully understand yet. Every detection reveals how matter moves under the most extreme conditions imaginable. And the future of gravitational wave astronomy is even more astonishing. Scientists are planning space-based detectors like LISA, the Laser Interferometer Space Antenna. Instead of detectors on Earth, LISA will place spacecraft millions of miles apart in orbit around the Sun. The system will measure gravitational waves from supermassive black holes millions or billions of times heavier than the Sun. These giant black holes sit at the centers of galaxies. When galaxies collide, their central black holes slowly spiral toward each other over millions of years. Eventually they merge, releasing enormous gravitational waves powerful enough to shake entire regions of spacetime. LISA could detect those waves from across the observable universe. It might even detect relic gravitational waves left over from the Big Bang itself. If that happens, humanity could potentially observe motion from the earliest moments after the universe began. Not light. not matter. Motion in space-time itself. Now think about how strange this really is. Right now, at this very moment, gravitational waves are probably passing through your body. Ripples from distant black holes. Ripples from exploding stars. Ripples from cosmic events that happened millions or billions of years ago. You can't feel them. Your atoms move together with the wave. Everything stretches and compresses together. Just like Earth's motion through space feels invisible because everything around you shares the same motion, the universe is constantly vibrating with motion on every scale imaginable. Let's go even deeper. Motion doesn't just affect stars and galaxies. It affects the shape of time itself. Near massive objects, time slows dramatically. This effect is called gravitational time dilation. The stronger gravity becomes, the slower time passes. Near Earth's surface, the effect is tiny. But near a neutron star or black hole, it becomes extreme. A neutron star contains more mass than the Sun compressed into a sphere only about 12 miles wide. Its gravity is so intense that escaping from its surface would require speeds approaching half the speed of light. Time near a neutron star slows noticeably. If you stood on the surface of a neutron star for 1 hour, more than an hour would pass for someone far away from the star. Near a black hole, the effect becomes even more dramatic. At the event horizon, gravity becomes so strong that time nearly stops relative to distant observers. This isn't an illusion. It's a real physical effect predicted by Einstein's equations and confirmed experimentally. The movie Interstellar actually used scientifically accurate calculations for this effect. On the planet orbiting close to the black hole Gargantua, 1 hour passed for the astronauts while about 7 years passed for people farther away. That sounds like science fiction, but the physics behind it is real. Black holes are extreme engines of motion and gravity. They warp space. They warp time. And they influence everything around them. Stars orbiting near the supermassive black hole at the center of the Milky Way move at incredible speeds. Some travel thousands of miles per second. Astronomers have tracked these stars for decades. By measuring their motion, scientists prove that a supermassive black hole exists at the galactic center. That black hole is called Sagittarius A star. It contains about 4 million times the mass of the Sun. And our entire solar system is orbiting around it right now. Every planet, every ocean, every mountain, every human being, all circling an invisible monster at the center of the galaxy. And yet we never notice. Because motion itself is relative. Now consider another incredible fact. The atoms inside your body are never truly still. Even if you sit perfectly motionless, the molecules in your body vibrate constantly due to thermal energy. Electrons move around atomic nuclei. Atoms collide with each other. Quantum mechanics tells us that particles can never have perfectly defined position and momentum simultaneously. At the deepest level, reality itself is restless. Nothing is perfectly stationary. Absolute stillness may not even exist in nature. The entire universe appears built upon motion and change. Galaxies spin. Stars orbit. Planets rotate. Atoms vibrate. space expands. Even empty space fluctuates with quantum activity. Motion is woven into the structure of reality itself. And despite all of this movement, the universe also follows remarkable patterns and order. Planetary orbits remain stable for billions of years. Galaxies form elegant spiral structures. Gravity organizes matter into stars and solar systems. Are wormholes possible? Could faster-than-light travel somehow exist through warp spacetime? We don't know. Modern physics is incredibly successful, but incomplete. Physical laws remain consistent across unimaginable distances. The same laws governing falling apples on Earth also govern colliding galaxies billions of light-years away. That's one of the most extraordinary discoveries in science. The universe is understandable. Not perfectly understood. Not fully solved. But understandable. Tiny creatures on a small rocky planet evolved enough intelligence to uncover the laws controlling stars, gravity, time, and motion across the cosmos. We figured out that Earth moves around the Sun. We discovered that the Sun moves through the galaxy. We measured the expansion of the universe. We detected gravitational waves from colliding black holes. We built machines capable of measuring time to accuracies of billionths of a second. And all of that knowledge came from curiosity. From looking upward and asking questions. How fast are we moving? Why can't we feel it? What is space? What is time? Those questions transformed human civilization. And we're still asking them. There are mysteries we still don't understand. What exactly is dark matter? What is dark energy? Why does gravity exist at all? Can space-time be unified with quantum mechanics? And perhaps the strangest part of all is this. Everything we've discussed tonight, every speed, every orbit, every galaxy, every black hole, every ripple in space-time, is happening inside a universe that may itself be only a tiny piece of something even larger. Because modern cosmology suggests that our observable universe might not be the whole universe. It may only be the portion we can see. The observable universe is limited by the speed of light and the age of the cosmos. Light has only had about 13.8 billion years to travel since the Big Bang. That creates a cosmic horizon. Beyond that horizon, there may be vastly more universe. Possibly infinite amounts of space. Possibly countless other galaxies forever unreachable. Possibly regions where the laws of physics are different from ours. Some theories even suggest the existence of multiple universes, a multiverse. In certain models of cosmic inflation, space expanded faster than light during the earliest fractions of a second after the Big Bang. Tiny quantum fluctuations were stretched to cosmic scales, eventually becoming galaxies and clusters of galaxies. But inflation may not have stopped everywhere at the same time. Some regions of space may still be inflating even now, creating separate bubble universes disconnected from ours. Each bubble could contain different physical constants, different stars, different chemistry, different realities. We don't know if this is true. Right now it's theoretical, but the equations allow the possibility. Think about how extraordinary that is. Humanity went from believing Earth was the center of everything to seriously considering the possibility that our entire observable universe might be only one small region in a much larger cosmic landscape. And still, even if there are infinite universes, motion remains fundamental. Everything evolves. Everything changes. Entropy increases. Stars burn fuel and die. Galaxies collide and merge. Black holes slowly evaporate through Hawking radiation over unimaginable timescales. Even protons themselves may eventually decay if certain grand unified theories are correct. Nothing lasts forever. The universe is dynamic. Now let's imagine the far future. Not thousands of years from now. Not millions. Trillions upon trillions of years into the future. The stars themselves will begin disappearing. Right now the universe is still relatively young. There are hundreds of billions of stars in galaxies like the Milky Way, and new stars are still forming from clouds of gas and dust. But star formation won't continue forever. Eventually galaxies will use up most of their available hydrogen gas. Without hydrogen, no new stars can form. The universe will slowly grow darker. Red dwarf stars, the smallest and longest-lived stars, will survive the longest. Some may burn for trillions of years. For comparison, the universe today is only 13.8 billion years old. A trillion years is almost unimaginably farther into the future than the present is from the age of the dinosaurs. During that era, the night sky would look completely different. The merged Milky Way and Andromeda galaxy may be one of the only visible galaxies remaining. Everything else will have disappeared beyond the cosmic horizon due to expansion. Future civilizations, if any exist, may never know other galaxies once filled the universe. Eventually, even the last stars will die. White dwarfs will cool into black dwarfs. Neutron stars will drift silently through darkness. Black holes will dominate the cosmos. This era is sometimes called the degenerate era. The universe becomes a graveyard of stellar remnants slowly orbiting each other in darkness. But even then, motion continues. Gravity still shapes trajectories. Objects still orbit. Black holes still collide. Over vastly longer timescales, gravitational interactions will eject many objects from galaxies entirely. Planets, stars, and remnants will be flung into intergalactic space. Galaxies themselves may slowly evaporate as objects escape through gravitational encounters. Then comes the black hole era. Black holes are incredibly long-lived. A supermassive black hole can survive for numbers of years so enormous they barely fit inside human language. But even black holes are not eternal. According to Stephen Hawking, black holes slowly lose energy through quantum effects near the event horizon. This process is called Hawking radiation. Over unimaginable spans of time, black holes evaporate. Tiny black holes evaporate relatively quickly. Supermassive black holes take vastly longer. Eventually, the last black holes may disappear in flashes of radiation. And after that? Possibly nothing but thin, cold radiation spread across an endlessly expanding universe. No stars. No planets. No galaxies. No life, just darkness approaching absolute zero. This possible future is called the heat death of the universe. Not an explosion, not destruction, just gradual fading, motion continuing, but with less and less usable energy available. The universe reaching maximum entropy, a state where no meaningful work can be extracted anymore. It's difficult to emotionally grasp timescales like this. Human civilization is only a few thousand years old. Recorded history is tiny compared to cosmic history. The entire existence of our species is less than the blink of an eye compared to the lifespan of stars. And yet here we are, able to calculate the possible fate of the universe itself. That alone is astonishing. Now here's something even stranger. The atoms making up your body today were once inside ancient stars. Hydrogen formed shortly after the Big Bang. But heavier elements like carbon, oxygen, iron, calcium, and gold were forged inside stars through nuclear fusion. When massive stars died in supernova explosions, those elements were scattered into space. Over billions of years, that material became part of new stars, planets, oceans, and eventually living organisms. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in every cell of your body. All of it came from dead stars. Carl Sagan famously said that we are made of star stuff. And literally, physically, that's true. Your atoms have already traveled unimaginable distances through the galaxy before you were ever born. Some of the particles inside you may be older than the sun itself. They've been part of ancient stars, part of interstellar clouds, part of exploding supernovas, part of Earth for billions of years. Now, temporarily, they're part of you. And one day they'll continue moving after you're gone. Nothing in the universe stays fixed forever. Matter changes form continuously. Stars become dust. Dust becomes planets. Planets produce life. Life returns material back to the cosmos. It's one long continuous cycle of motion and transformation. And when you really think about it, that changes how you see yourself. You're not separate from the universe. You are the universe. A temporary arrangement of matter and energy capable of awareness. A collection of atoms that gain the ability to think, to feel, to wonder, to ask questions about existence itself. That's rare. Maybe unimaginably rare. As far as we know, Earth is the only place where the universe became self-aware. Maybe intelligent life exists elsewhere. Statistically, it seems likely. There are hundreds of billions of stars in our galaxy alone. Possibly trillions of planets. And trillions of galaxies beyond that. The numbers are almost impossible to comprehend. Yet despite all our searching, we found no confirmed evidence of alien civilizations. This is known as the Fermi paradox. If intelligent life is common, where is everybody? Maybe civilizations are rare. Maybe intelligent species destroy themselves. Maybe interstellar travel is too difficult. Maybe the distances are simply too vast. Or maybe advanced civilizations exist but are separated by cosmic timescales and never overlap. The galaxy is enormous. Even traveling at light speed, crossing the Milky Way would take about 100,000 years. And relativity creates strange consequences for long-distance travel. Civilizations separated by thousands of light years may effectively live in different eras of galactic history. Communication itself becomes incredibly slow. A message sent to a civilization 10,000 light years away would take 10,000 years to arrive. Their reply would take another 10,000 years. Entire civilizations could rise and vanish between conversations. The universe may simply be too large and too old for civilizations to easily connect. And yet humanity keeps searching. We build radio telescopes. We scan the skies for signals. We search exoplanets for signs of atmospheres and possible life. We send probes into space carrying messages about humanity. The Voyager spacecraft, launched in 1977, are still traveling outward today. Voyager 1 is now over 15 billion miles from Earth. It carries a golden record containing music, sounds, greetings, and images from our world. Long after humanity is gone, Voyager may continue drifting through interstellar space. For billions of years. Possibly forever. Think about that. A tiny machine built by primates on one small planet is now traveling between the stars. Humanity reached beyond Earth. Even if only barely. And maybe that's the beginning of something larger. Right now we are a young civilization. Space travel is still primitive. We've only walked on one other world. But technological progress can happen astonishingly fast. Just over a century separates the first airplane flight from reusable rockets and space telescopes capable of seeing galaxies billions of light years away. What might humanity achieve in another 1,000 years if civilization survives? Fusion energy? Interstellar probes? Artificial gravity? Generation ships? Permanent settlements on Mars, Europa, Titan, or planets around other stars. Maybe one day humans or our descendants will spread across the solar system. Then across nearby stars. Perhaps someday entirely new branches of civilization will emerge among different star systems. Human culture evolving separately across light years of distance. Different worlds, different skies, different histories, all carried forward by beings descended from people who once looked up at the night sky from Earth and wondered what was out there. And if that future happens, motion through space won't just be a scientific fact. It will become humanity's destiny. Because Earth itself is temporary. The sun is temporary. Eventually, survival may require moving beyond our home planet. Beyond our solar system. Beyond our galaxy. The story of life may ultimately become a story of migration across the cosmos. Or maybe not. Maybe humanity remains confined to Earth. Maybe civilization ends long before reaching the stars. We don't know. The future is unwritten. But regardless of what happens, one thing remains true. At this very moment, you are alive during one of the most extraordinary periods in cosmic history. A time when the universe is visible. A time when stars still shine brightly across the sky. A time when intelligent beings can uncover the laws of physics and understand the cosmos. A time before the distant galaxies disappear forever beyond the horizon. You exist in a brief window where the universe can still be explored and understood. That's incredibly special, and despite all the darkness, all the vastness, all the terrifying scales involved, the universe is also astonishingly beautiful. Nebulas glowing with newborn stars. Ringed planets drifting through darkness. Galaxies spiraling like cosmic hurricanes. Auroras dancing above polar skies. Black holes bending light itself. The universe is violent, but also elegant. Chaotic, but ordered. Cold, yet capable of producing life and consciousness. And somehow, out of all this motion and matter and energy, you appeared. A conscious observer riding on a moving world, a tiny part of the cosmos able to reflect on the cosmos itself. That's not meaningless. If anything, it gives meaning. Because meaning isn't something the universe hands to us. It's something conscious beings create. Through curiosity. Through exploration. Through relationships. Through art. Through science. Through wonder. The universe may not care about us in any human sense. But we care. And that caring matters to us. So tonight, when you close your eyes, remember where you truly are. You're not in a silent, motionless room. You're aboard a rotating planet orbiting a star moving through a galaxy racing across an expanding universe. Every heartbeat carries you thousands of miles through space. Every breath happens aboard a world traveling at impossible speeds. You are participating in a cosmic journey billions of years in the making. And despite how enormous the universe is, despite how small we are within it, you are one of the rare parts of the cosmos capable of awareness. Capable of understanding. Capable of wonder. The atoms inside you are forged in stars. The light entering your eyes crossed unimaginable distances. The thoughts inside your mind are products of a universe evolving toward consciousness, and for a brief moment in cosmic history, you get to experience it. You get to be here. Alive. Aware. Moving through the stars.